Hi, everybody. Welcome to our webinar on Spark and Machine Learning for Data-Driven Marketing. We have three panelists with us today. We're going to start with Joe Caserta, who is the president of Caserta, followed by Max Goldblass, director of Caserta Labs, and finally, Mark Labrie from Databricks, who is partner engineering solutions architect. We're going to get started with Joe, who's going to give us an overview.
Hi, everybody. This is Joe Caserta. Going to talk a little bit about using machine learning in order to figure out how to optimize the path to purchase for customers. And we're going to do it over a course of an hour. And within that hour, we're going to talk high level about the ultimate goal and the addressing the problem. Then we're going to talk a little bit about the architecture of the solution, and then get into the science part of it. So we'll start with, let's just do an introduction of Caserta first. You know, Caserta is a consulting firm. Data intelligence, strategic consulting is all we do. We build data lakes, data warehouses, data laboratories, data science solutions, and data engineering solutions, providing our customers with very strategic data initiatives to solve interesting problems with data. We also host a meetup that is local in New York City that gets streamed on Facebook. The next one we have is actually on Pi Day, March 14th, 3.14 for Pi. And we have about 5,000 members. It's a great event if you're in New York City. It's downtown on Spring Street this time around. We're going to do more machine learning, talking with IBM. And it's also going to be streamed. If you're interested in attending this, you can reach out to Remy, R-E-M-Y, at Caserta.com. He could put you on the list. So for today, we're going to talk about the customer journey. So what the customer journey means is, as we go through the cycle of reaching out to people to try to get them engaged to do business with us, there's a whole bunch of touch points. Every one of those touch points is really important, because each one of those touch points costs money, costs time, costs resources, and may or may not be effective. So, so what we're trying to do, because we can now with technology, is capture every single touch point that touches, that connects a person or another business with your business. And so what we did is we went through the 5 different steps of making a sale or keeping a customer, making a customer aware of your business, making a customer consider purchasing your business, something from your business, making the actual purchase of something, services or goods, retaining that customer through customer service, and then having that customer become loyal, right? That's really the goal of this exercise. So we'll walk through a bunch of different touch points. We're not going to do all of these. I think Max has 4 prepared. So we'll go through how to do things like, you know, figure out if they're clicking on the website, if they're responding to emails, if the customer loyalty program is working, and then be able to figure out, of all of these different touch points, which ones work, which ones doesn't work, and also the quantity of touch points. So, you know, if you're sending 1 email or 10 emails, you know, is 3 good, is 4 good, is 5 good? At what point is the saturation point? So, so that'll be pretty exciting. And that's new and different because we weren't able to really do this before. You know, what we used to do through the legacy of path to purchase analytics is we used to have to make a rule to say, you know, do we want to, like, it was a binary decision. Do we consider the first touch point, where we actually get a customer to understand that we exist and a product exists? Is that really the main attribution of making a sale? Or is it the very last touch point that actually gets that rings the cash register, is that the most important attribution of the journey that makes a sale. And most attribution models were built around that. And then as technology got a little bit more mature and marketing got a little bit more mature, we started to be able to at least capture a lot of the different events that were happening. But the technology around statistical analytics and data analytics in general wasn't terribly mature until recently. So what we were doing in the meantime, we were just collecting all of the different channels of connecting with customers, and then basically dividing them across evenly, so that, you know, if you were to send out emails, mailings, and banner ads, you would just divide it. You know, if there were 3 of them, they would all get a third. If there were 10 of them, they would all get a 10th of attribution. But now, you know, now that we have technologies with machine learning and Spark and cloud technology that can handle the volumes of data from every type of customer channel there is. So now we can collect all the data, we can analyze all the data, we can look for the full complete behavior pattern of every single customer, consider all of the touch points, and then build models, algorithmic models that can do stats on figuring out exactly which mailings, which emails, and which ad clicks are effective and which aren't effective. And then we can tune the machine to optimize what is the most optimal path to purchase. So of all of the different channels, what works and what doesn't work, and then come up with a winning combination to optimize your path to purchase and your customer's journey to purchase. So in order to do this at the enterprise level, a few things has to happen. First of all, we took a standard called CRISP-DM, stands for Cross-Industry Standard Process for Data Mining, and we kind of adopted it towards doing data science. And it's very, very, very methodical and very repeatable. And you know, when you have a startup or you have just a marketing department, you don't have to be as rigorous with your standards, but when you're trying to deploy these types of solutions across an enterprise, standards are very important, and being methodical and disciplined in your solutions is also very, very important. So we came up with 6 steps, and I'm not going to go do a deep dive. If you're interested in CRISP-DM and data science for the enterprise, I'm actually teaching a half-day course in person in Boston on May 22nd at the Data Summit. So you get like 4 or 5 hours of just these 6 steps on how to follow this process. But at a high level, first thing we want to do is we want to make sure that we understand the problem we're solving. We want to do data discovery, data munging, and data profiling to figure out, what are the data anomalies? What is the data that we're actually dealing with? Is it credible? Is it usable? And then we would need to prepare this data. Traditional ETL, right? You're getting data from 10 different data sources. Someone, someplace, somehow, we need to still harmonize all of this data before we can stitch it together to figure out that path to purchase, right? In order to know the customer journey across 10, 20, 30 different channels, we need to first of all figure out how to identify the customer across all of these different channels. And that, in this entire project, step number 3 is probably the most intensive one. That's the one where, for the use case we're going to talk about, we actually had to do a sub-project called identity resolution, where we had to build a graph data frames in Spark in order to connect all of the different customers, customer IDs for the same customer across all of these different channels, and do some deterministic matching and some probabilistic matching, which Max will get into in a couple of minutes. And then once you have all of your data harmonized and stitched together, then you could build your models. Building the models, we use Spark, and then we go through and we evaluate the models, whether actually they're sensible or not, which takes domain expertise. So far we've done some business understanding, some data engineering, some data modeling, some data preparation in ETL, and some data model, and then some data science predictive models. And now we're doing domain expertise for the business. So typically, I mean, it's a lot to do for a single person or even a single group. So we built a small team for all of these different disciplinary specialties, and we built an agile Scrum team to do this all together. And then finally, when it's done, then we want to be able to deploy this to production. And I mentioned on this slide PMML because in our case, we didn't need to go to PMML because we did everything in Spark. But there are times when you're doing things at the enterprise level, you'll have data scientists that sometimes like SAS, sometimes like R, sometimes like SPSS, and sometimes like Python. PMML is the predictive model markup language that unifies all of these different models. And then you can go from whatever flavor that you like to PMML to whatever flavor that you want to implement in production. Use it with caution. It's not always perfect, but it is an approach to take if you have heterogeneous models out there in your enterprise. So once we have the process done, now we have to persist the data. So we do this with what we call the data pyramid. So we have 4 tiers within the data pyramid. We have the landing area, which brings all of the data from the sources in full fidelity and sits it down for everything else to be downstream. This area is locked down. No one accesses it except for the processes that loads the data and the processes that reads the data. No human intervention in this area. So it collects metadata. It has information lifecycle management, things like how long we can keep it, how long are we not allowed to keep it, those types of rules, and then it is secure. From there, we have our data lake, and our data lake is a somewhat governed, somewhat structured environment that is typically an object data store. In this case, this was 100% AWS solution, so it was on S3, our data lake, and what it does is it takes the data, all of the event data from the landing area, and then all of the reference data from the data warehouse, because we need to be able to put context around all the information that's coming in that we need to do science on. So this, in the data lake, we're applying some data quality. We're doing data quality monitoring. We're applying more metadata. We're putting it in a data catalog. Information like lifecycle management, and of course data integration. So the entity resolution that I talked about in the last slide, in the landing area, it's all disparate data, right? Joining it together really would be pretty close to splitting atoms. In the data lake, it's trivial, right? Because we built a mechanism that unifies all of the data using graphemes. And then, so now we have our data lake built. So now we can build ephemeral data science workspaces where we can, stand up a cluster in Spark and start building some models, start munging some data. And, if we like it, we can promote it either back to the lake or to the data warehouse. If we don't like it, after 90 days, it just gets shut down and it disappears. So it's very good. It's a very good environment and ecosystem to manage your infrastructure where you don't have a bunch of shadow IT departments. If the data is good, it needs to be promoted into the enterprise data lake or the enterprise data warehouse. It cannot sit in the data science workspace for more than 3 months because then it will go away. Once it is promoted, then it's available in a fully governed, fully structured data warehouse. In this case, we used Redshift. And on top of Redshift, we were using Tableau for users for the through business intelligence. And we also built some microservices that reads data directly out of the data lake to integrate with other applications. And this is what the infrastructure looked like. So we had a bunch of data sources. We had campaign data, sales data, weblog data, DMP data, different ways of ingesting data depending on where the data was coming from and the frequency of data and the latency requirements. And then within S3, we had our data lake. And we had two tiers of our data lake. We had the first tier, which looked very much like the raw data. And then the second tier, which we call design data, which looks very much like the data warehouse. By design, we build all of the structures that live in the data warehouse in S3 first, and then we push them out to Redshift for consumption. So Redshift can be shut down and restarted, and you would not lose any data. You would just copy it back out from S3. All of the ETL, all of the data science, and all the data integration, cleaning, matching, deriving, aggregating, preparing, everything was done within Spark. And in this case, we used Databricks for the entire Spark implementation. Databricks is really great because it manages the clusters for you. So it's one less thing to think about when you're doing these types of projects. And it also enables collaboration when you're doing data science. And then we also had, in this case, there are many different data catalogs out there. Elation is one of them that we use quite often. But in this case, CCAN, which is an open source Python-based data catalog, which works great. We also use Lambda functions to capture all of the metadata about the data sets that we're receiving in S3, and then we were putting them in a repository that we custom made in Redshift so that users knew when the data was available and what the data was about. And so now we have the environment ready, right? So now we went through all of the data processing, all of the data preparation, and it's sitting in the laboratory just waiting for consumption for someone to build models. And now we're going to go over to Max to talk about the models that he built. Anyone want to reach out for the questions? Here's my contact information. Feel free to reach out to me directly.
Thanks, Joe. That was great. We're now going to turn it over to Max, who's going to go into the processes.
My name is Max Goldbass, and today we're going to be talking about multi-touch attribution modeling with Spark. So I'm a data engineer at Caserta. I lead up also the Caserta Innovation Labs. I say that I'm a data engineer mainly because I like the data engineering side of things. I like the infrastructure side of things. At the Caserta Innovation Labs, we get to play with all the new infrastructure projects and tooling and software that come out, and we get to try to keep ourselves on the cutting edge. And it's a lot of fun. I like it a lot. Me and my team get to really dive into new and exciting and fun products. Today, we're going to be talking about multi-touch attribution. Multi-touch attribution really means that when you want to attribute ads to getting users to do actions, getting users to do actions is called converting them or getting them to convert. So attribution is the practice of getting ads attributed to those conversions. So multi-touch just means that you are getting many different touch points and many different ads to convert to be attributed to the same user to get them to convert. I know that sounds a little confusing, but we'll come back to that a little bit. So data science with Spark. Spark is a parallelizable analytics engine, which that means that it really is able to scale out very effectively. So it doesn't really matter what the data size or data workload is. Spark can just take on more machines until the job can be handled. This job can be large-scale data processing, aggregations, or machine learning, and we'll talk about that today. So the background is I worked on a cloud migration for a large media client. They could not be with us here today, but they were using older technologies. They were using kind of stuff that was really kind of designed in the 80s, and we have new stuff today to work with. They were not also familiar with Spark. They really weren't familiar with what it could do. They were using older software to do their analytics and their machine learning. So we wanted to show them how Spark's ability to really jump on big workloads and parallelize itself is very powerful. And we also wanted to show how it could do machine learning very quickly and easily and effectively. So we built them this model. This model is being compared against their current models that they're using in their analysis and their predictions. So they're comparing the two right now. Hopefully it'll be put into different production and compared up against what their current practices are. We're pretty confident, though, that they'll be impressed by how well it performs. So our objectives today are we want to see which touch points drive engagement in our rewards program. So in this case, the conversions that we were talking about earlier are getting people to interact with a rewards program. And so the rewards program has several different ads for it. People get actual physical mail. They get text messages to their phones. They get events they can actually go to that are part of their rewards program. And they also get emails, and we can track site activity. All this, we want to see which is most effective at getting them to engage with the rewards program. We also wanted to get them excited about the infrastructure that we built for them. So one of the really cool things that I'm pretty proud of is the identity resolution that we did. This identity resolution enables them to match up all the different data sources into one data key per user. So what that looks like is you take the cookies, you take the emails, you take the names, and you kind of bind them all together. And once you bind them all together, you can add a key to that binding, that clustering. And once you have that clustering, you can use that for your analytics. You can actually look for users across different channels and different forms of attribution. This identity binding gives everything a one place to go look for all your data. So all the data is in one data warehouse. This one data warehouse has all the different types of events in it, and it gives you the ability to go to one place for all your data. So data scientists are really they're pampered. We gave them everything they needed to do their jobs, and we're pretty proud of it. What does this infrastructure look like? This infrastructure looks like a data lake access via Databricks. So data lake is a bunch of files that are stored that act like a database, but they're not. But it scales out really well. So you can have a lot more data in a data lake for a lot less money. It's about cents on the terabyte for S3. This Databricks also manages all of our Spark clusters. So Databricks invented Spark. Spark has since been adopted by most of the big Fortune 500 companies, and all of the major cloud providers, Google and Amazon, provide a Spark cluster. Databricks also invented Spark, and they open sourced it. So their managed Spark solution is the best. They kind of have a couple unique twists on their managed service that we were happy to enjoy. And the graph data frames mastered all the data and clustered it together into one main spot that gave everyone the key. It matched up the cookies and the emails and everything into one key, and that was what Databricks provided us. So for AWS, like I said, the data lake was in S3. This is a bunch of Parquet files. Parquet files are really just fancy file objects that can read and write very easily, and they're really great to use for doing large processing. Amazon also has their data warehouse, which is Redshift. This data warehouse has the ability to parallelize, unlike other databases, and it can get very, very big. So this was the main source for our data for today's analysis. And then they also have their compute infrastructure, which is Elastic Cloud Compute, EC2, for the clusters. So Databricks doesn't have to manage actually getting servers and data centers. They can just get all their machines from Amazon Web Services, which is a nice little thing for Amazon and Databricks to work together for. And then Caserta gave them a task manager, which is an Airflow. That is to the right here. You can see all the tasks. Every task is dependent on a previous task, so we were able to orchestrate all of the tasks accordingly. Docker provisioned Airflow, so made sure that it was easy to deploy Airflow instances. And then RabbitMQ gave us the ability to queue up messages. So we didn't want to send too many jobs to the Spark cluster all at the same time. So RabbitMQ allowed us to queue up the jobs, and as one job finished, you could add another to the queue. So we wanted to get all of our data into one kind of concise format. This looked like getting all the touch points that happens in between conversions. So like I said, conversions are interactions with the rewards program, and the ads are the interactions are all the ads that they see in between every one. We then wanted to get everything into kind of one row per path. So what does it look like? We needed to get all the engagement data. So the engagements, like I said, are texts, emails, member events, a couple other different channels, but those are the main ones. And then we want to pull all conversions by individual key and by event type and date. We didn't really care if the same user did the same event, the same conversion several times in one day. If they, for example, redeemed 4 or 5 coupons in the same day, we just don't really care because we want a conversion path that says every different event um, is every group of events more or less on the same day by the same user by the same event type is all the same conversion path. This kind of cleared up a lot of the noise in our signal. So, like I said, conversions are the events that happens, and the total analysis for this data was about 15 billion rows of event data. That was a lot of data, but Spark is able to handle that workload. As long as you just give it the instances that it needs, it can just take care of all of it. So we wanted to get all the data into the from all the events, every row was an event, into one row per path. So this looked like flagging every individual and then flagging every conversion path. So we wanted to have every time a path broken up by users and then by conversion events. Then we could say all the events that happen between every conversion, we can aggregate out and get a path from that. So once we had everything in a path format, which was all the events that happened and whether or not the conversion happened, we can then make our models. So this is what we hypothesized, and this is what we pursued. So what does that look like? That looks like you can see several different conversion paths ordered by individual key. So the individual key is, like I said, the graph data frame mastery. So it's able to match up all the users across different channels and determine which person they are. So this looks like saying, okay, this first user got an email, then got a text, and then they converted. So then we can say that that email and that text can be attributed to this conversion. Um, then afterwards, they got another email. However, between that email and today, they have not converted again. So we can say that conversion path was not successful. The second user is a different conversion path, obviously, because obviously no two users are on the same conversion path. So they got a text and then they converted. Then they got a text again, and they haven't converted since that last conversion. So we know that conversion is unsuccessful. So now that we have all the activity and the conversion path, we can actually just aggregate by conversion path. So once we have everything aggregated by conversion path, we can say, okay, how many emails did they get? How many texts did they get? And this is for a bunch of different channels as well. We're not just considering emails and text, but for this example, please bear in mind. But then we have all of our data really in kind of more of what we're looking for. The only thing we got to do afterwards is add whether or not they converted. If they converted, we can say with confidence that that was a successful conversion path and that the ads that they saw, we can attribute to that conversion. Like I said, this is multi-touch attribution. We are saying that the emails that they got and the text that they got can attribute to that conversion by their individual key. So this is what our data really looks like. Once we have the data looking like this, we can just turn everything into our analysis data. This is really looking exactly like what we want to see for machine learning. We have all of our features, so everything that indicates whether or not we want someone to convert and whether or not they did convert. So we can do logistic regression. Logistic regression really does work well for a lot of data science. It's fairly computationally inexpensive. You can do a lot of models with it very easily, very quickly, and it's not too hard to use. So many data scientists will go to logistic regression first to have a soft approach and soft look into their models, but it'll also give you pretty accurate results. However, the main thing, first of all, the main thing we saw was that email and web traffic were king. They got a lot of emails, they got a lot of web traffic, so we could say that there was a good amount of attribution for the emails and the the web traffic they did, the activity that they did on the website. That would definitely indicate whether or not they were going to convert. However, this model is kind of incomplete and missing one large thing, and that is time. Logistic regression does not take time into account, at least the way we are modeling it by conversion path. So what we wanted to do is we wanted to weight it against whether or not the amount of ads that they saw were really equivalent to the analysis that we did. So we could say we would want to do a survival analysis to say whether or not we believe that the number of ads that they saw, they would survive the next incremental ad. So if they got 6 emails, after the 7th email, or will they survive? Will they not convert again? And this was based on time. So survival analysis can actually weight against our additional weights and determine whether or not it would work. Whether or not 1,000 ads over 1 year is 10 times greater than 100 ads in a week. We wanted to determine whether or not that was true. Survival analysis gives us a parameter by day. So the highest survival rate was web traffic. We found that they would really not convert based on the number of ads that they saw and the amount of time, so they could keep on surviving, getting more and more ads via web traffic. So that really kind of hit web traffic pretty hard and determined that web traffic wasn't as important. So what does this look like? This looks like we get a survival probability based on the duration. So every survival probability was based on the channel and the duration of the days. So we can say that, okay, for 6 days, the survival probability is pretty high, right? They got only 13 emails in 6 days, which is actually kind of a lot. But that was about the equivalent of about 12 emails with weighted for days. However, if they got 13 emails in 30 days, we could probably say that these emails were more or less impactful. We would say probably less impactful because they obviously survived a lot longer. But however, since they survived longer, they actually get to see them survive. The survival probability is thus lower. You can see actually for if they got 52 emails in a duration of 345 days, which is obviously less emails per day, the survival probability is pretty low, meaning that they probably are going to convert pretty soon. But it actually weighted up the emails a little less than the total impact that was kind of delayed. You can see 40 emails goes down to 24 emails over 214 days. However, 52 emails goes down to 16 emails, so it wasn't as kind of impactful. The 52 emails versus the 40 emails. So that survival analysis weighted our email parameter appropriately, and we were able to do another logistic regression model based on that. And that kind of gave us a better insight as to whether or not we could do our logistic regression based on weighting of the model. So we use these weights that are based off the time survival analysis. These weights since have been readjusted by duration and using each parameter for each channel. This actually was able to give us a better insight into how each aggregation of events was really worth what they were worth based on the amount of time that someone saw them, because as the time would go on, you would obviously remember less and less of these events. So from this analysis, we determined that email and events were king. We found that the best engagement with the rewards program were whether or not people were going to the events, and again, whether or not they were getting emails. This actually makes sense because events are more likely to get a user base around the usage, but however, the events were significantly less than the number of total events that they saw in aggregate versus the number of total events they saw for something like web activity or display ads was significantly less. So further analysis, we would definitely do a univariate analysis on this. We would like to we'd like to do a multivariate analysis. We did a univariate analysis. We looked at all the parameters only by single channel. Multivariate would demonstrate how different different types of survival analysis would work together. We really weren't able to incorporate that properly today, not with our current model, so we didn't really use it. Also, we didn't have social media data. We would like to integrate other forms of social media data, especially Facebook, Twitter, the main kind of popular social platforms. The LinkedIn probably wouldn't have worked, nor would like Snapchat. So definitely Twitter and Facebook. And then the other one was definitely to use deep learning. Deep learning is a different ball game when it comes to machine learning. It really requires a lot more computational power. It requires a lot more fine-tuning of parameters, so we didn't really go into this. But however, we did have the amount of data that would really be necessary. We do believe that we could use a neural net to get the correlation between how different channels work together and to kind of classify how users interact with various touch points. So, in conclusion, we would like to enforce that you want to use technologies that can use more machines or can parallelize. So Redshift, it can use more machines. Spark can use more machines. And this is really where technology is these days. We need big data technologies that can parallelize and consume large amounts of data. In your analysis, definitely watch for your bottlenecks. Spark can kind of choke up when you do certain operations. These operations are mainly like to aggregate everything into one number. We had to do that for some of the duration counts, and for some of the other counts we had to do. Those cost a lot of time. So just try to know where they are and use them less. But the survival analysis was also good on its own. It did tell us a good amount of data, and we were happy to use it, happy to have it in there. And caching for your data really helped with saving the data in RAM. There's two different types of memory. One is actually memory in your storage. The other one is memory in your RAM, in your random access memory. Spark takes advantage of RAM by doing all the analytics in the RAM. RAM is significantly faster, but a lot more expensive. But if you cache your data, you can actually put all the data into the RAM for a little while, and accessing it and playing around with it is easier and faster. However, it will go away as soon as you turn off the cluster. So caching can definitely help you store an aggregated version of your data or a sampled version of your data a little more forward. Pretty useful, definitely pretty useful, especially in sample sets. Thank you for joining me today. I had a lot of fun with this analysis. I really enjoyed getting into Spark and kind of seeing what I could do. It was fantastic to show our client how everything works with this. And yeah, if you have any questions, please reach out to me. My name is Max Goldbass. Thanks for joining us today.
Thank you so much, Max. We're now going to continue on with Mark from Databricks, who's going to go into how Databricks fits into the mix. Mark, take it away.
All right. Thank you, Remy. Yeah, so I got about 15 minutes here to cover. Actually, Remy, do you want to make sure I have the right screenshot up there? But I have about 15 minutes here just to cover Databricks as a product, sort of the. What's that?
Your screenshot looks good. Yep.
Fantastic. Thank you. Yeah, I just wanted to cover the components of our product at a high level, which enable folks like Caserta, Max, and Joe to confidently and reliably implement big data analytics at scale inside of their customers. For those of you on the phone who are already implementing some big data analytics, maybe using things like R or Python and open source technologies, you're familiar with how difficult it can be to actually implement the solution end-to-end with all of the complexities involved. So what is Databricks as a company? We're a unified analytics platform powered by Apache Spark, which we call the Unified Analytics Data Engine. I'll get a tiny bit more into that for those of you who are unfamiliar with Spark. Our company goal is to really unify the collaboration between data science, data engineering, and the business, so that way they can work together to develop those game-changing projects and those data and analytic projects for them. We are the founders of Apache Spark, or I mean, I didn't found Apache Spark, but the folks who built the company did found Apache Spark. As a company, we still contribute 75% of the open source code, which is 10 times more than any other company, and we've trained 90,000 plus Spark users on this platform. So we're very much the leaders in the Spark ecosystem. So I won't, hang on here for too long, but one of the main components of implementing big data and analytics that I talk about with my customers is that you really need to have fast lines of communication between the business, data engineering, and the data scientist in order to create products that will positively influence the company. It's when you really can integrate with the business that you can get clear, defined, measurable business value, which allows you to then build your big data analytics practice. So reducing the complexities of implementing big data analytics is critical in order to help those communication pipelines. What makes big data analytics difficult to solution? If you're not using a platform as a service and you're using open source tools, you have to worry about the setup, managing the infrastructure, and then learning how to optimize and tune technologies in order to fit your analytics needs. There's data pipeline complications where you need to make sure your data is fresh and it's up to date, and you're not going from tool to tool to tool, having to clean, change, and then insert data into other tools, which can increase the complexity. Especially if you're using streaming data, information tends to become stale and a lot of times unreliable if you're building multiple data science projects off of data. Not to mention that, but typically it'll take a data scientist and data engineer working in multiple different technologies in order to complete a solution, where the data engineer might be working in Hive or SQL, and then the data scientist is working in Spark or R or Python. In order to create your actual pipeline or data and analytics solution, you'd have to combine many different products and then have to account for that, especially at the speed at which you're communicating with the business. If it takes, from the first business meeting, you have to wait 2 months or a month in order to get back to them to show them what you've found and investigated in the data, you can lose a lot of velocity that's required to get the business excited, and you'll find yourself maybe recounting, past details of meetings that are really slowing down your innovation process. So for those of you who are unfamiliar with Spark, at its core, it's a big data cross-cluster computation engine. It's designed to make working with big data interactive, and on top of that hyper-fast engine, we have APIs for R, SQL, Python, Scala, and Java to work with that engine. So for folks from all different types of data working lives, they can interact with Spark's compute engine. On top of that, we have some high-level components. First is the Spark SQL and data frames. This is like a SQL engine for those of you who work in SQL to be able to do transformations and data pipelining. We have a structured streaming component where you can work with streaming data just like you would work with a data frame in Python or R. We have deep MLlib capabilities or machine learning capabilities with our MLlib API, and that allows you to do things like deep learning. And then we also have a graph analytics engine for those different types of relationship questions you need to answer. So before we get into a demo, I just want to set some context of the platform itself and why it makes implementing big data and analytics at scale. It makes it reliable and it makes it sustainable. So at the core of our platform, we have Spark as a compute engine. As you just seen, it can do all the different life cycles of your analytic needs. You can do the transformations, handle streaming data, and do machine learning, and serve it up to either an end user or a data product. It connects to all different types of data. You can connect to IoT streaming, cloud data. You can connect your on-premise data and then your Hadoop storages or object storages. The first component is that we have Databricks serverless. This manages the infrastructure and reduces the complexity of having to manage the different clusters and having to tune the clusters. In the demo, you'll see how easy it is to set up a cluster. There's Databricks Delta. This is a component that it makes your data pipelines reliable with things like ACID transaction and automatic indexing. A component of the big data and analytics lifecycle, which can take going from experimentation to implementation and production a significant amount of time. We have the Databricks runtime, and this is our version of Spark, or the open source Spark. It contains years of optimizations around Spark So we have the fastest Spark on the market with things like hyper fast connections to Redshift and S3. And then of course we have a collaborative workspace, which we'll go and see in the demo, so I won't hang on that for very long. All of this has enterprise level security around it. So if you're working with open source technologies, you'll know that securing them is sometimes a second thought to the open source community, especially since those aren't the key components of what their technology is about. With Databricks, we built security from the ground up. So what you're looking at right here is the home page of our platform. In the middle here, we have some getting started guides. If you'd like to go and sign up for the 14-day free trial, you can do that and get full access to our environment here. On the left here, I've got some directional places I can go to. For instance, if I wanted to create a cluster, I have the tab on the left here. We can go to create cluster, and you can see that I have the ability to create a cluster. I can see what types of runtimes that I want to use. I can set what type of server size I'd like. So depending on what type of work I want to do, maybe I want a driver node with a lot of memory or worker nodes with a lot of memory. And then we have auto scaling capabilities. So if I wanted to have a minimum of 2 workers, I could have a minimum of 2 workers and a maximum of 1,000 workers depending on the compute load that we had, or the computational load that's being put on the server. So that's just like that. You're able to create and stand up a cluster of however many servers you'd like. But let's get into like a notebook demo. We have a hierarchical folder structure here where we have our proprietary notebooks inside of. To create a notebook, you can create a notebook in either Python, Scala, SQL, or R language, and then attach it to a cluster. But as you'll see in the notebooks, you can actually create a notebook in, say, Python, and then switch over to using SQL if it makes sense for you. Across the top here, you can see that I'm connected up to a cluster. I actually do have the ability to view the code in a dashboard, but with the amount of time that I have, that probably wouldn't be the best use of our time. You have reversion history on these notebooks, and then you also have the ability, let's say if you train a model or you create a model, you can create a schedule here to go and train the model every few hours or every few days, weeks, or months. This is a huge help to taking something that you're building an experiment and putting it into production. So let's take a look at a demo workbook we have here. We're going to connect to some structured data in a SQL warehouse. We can pull it in. You can see that we have some product IDs right here across the, just a standard fake product data set. We can also connect to some object storage where you might be streaming data to, or you might just have some JSON data living inside of here. So if we connect to that JSON data, you can see that for every row, I've got some JSON fields here. Databricks or Spark comes with the ability to parse this JSON into a structured field. So you can see as I visualize that data frame, that JSON data frame, that it looks like a standard data frame or a structured table that we can then start working with. First thing someone might do is after connecting to the data is visualize the data set. So personally, I can flip back into SQL, join the different tables that I brought together, do some aggregations, and visualize the data. If it makes sense to visualize it in a bar chart, you can visualize it in a bar chart, or we have a number of different types of charts here that you can visualize them. And again, just showing off that you can use SQL or this isn't SQL, excuse me, this is the data frame logic. So depending on what you're most comfortable writing in, you have the ability to explore your data in it. So let's go and take a look at some machine learning or deep learning capabilities here. What we're going to take a look at is a shoe, or actually a data set of different shoes, and we're going to create a recommendation engine off of the shoes. The first recommendation engine that we're going to create is off of nearest neighbors. So this is a machine learning algorithm that many of you are probably already familiar with. But we can import this nearest neighbors from our Spark ML libraries. And if you take a look at the performance or the relative accuracy of what it would look like, asking, hey, I want this shoe, can you send me 10 other similar shoes? The nearest neighbor's algorithm isn't incredibly good. In fact, it's at least it's getting the fact that it's sandals in there. But we have the ability to reach out to other APIs and do some more advanced deep learning techniques with things like TensorFlow. Inside TensorFlow, they have something called the Deep Image Featurizer, which is like a transfer learning of sort, where you can take advantage of algorithms and models already pre-built for you, and then you can train it on your data and serve your data through it. So if we go and use this Deep Image Featurizer, you can see that our accuracy is improved tremendously. And I'm going through the code pretty fast, but you can see that we're not doing a tremendous amount of development work here just to create what I would consider, a production-ready model that you could implement in your organization. So here you can see some shoes, and we want to test the different types of shoes. One other demo that I thought would be interesting to show off is what it's like to work with streaming data inside of Databricks. So in this case, you can see that I'm telling Databricks what that schema of the table is going to look like. Just for context, this is a predicting whether or not something is going to be late depending on the work group it's in, for those folks who have to send people out in the field to do jobs. I tell Databricks that there's going to be an input stream table at this specific path. Expect that type of schema. I'm going to import a machine learning model. This is the model that I use to predict if each one of these live work groups are going to be delayed in what they're supposed to do. I transform that data right here, and you can see that if I actually print the schema that it's worked, I have fields like raw prediction, my prediction, the features, and label, which means I've transformed the data through a predictive pipeline, and now I have outputted results. So if we go and take a look down here, if I display that streaming table that I performed those predictions on, you can see where we've actually found some of these work groups which are likely to be delayed. So the relative height of this line just means the number of delayed work groups I have at this particular time intersection right here. So this is a relatively simple live graph, but all of our charts work with the live component as well. And then maybe after, if you want to work with your live data in real time, you can just write the table to memory, and it's going to update that table in memory, and you can work with it just like we were working with these charts up here above, or in the other notebook. You can start, aggregating and filtering to find some different nuances of the data to enhance the next machine learning or big data and analytic project. So in a nutshell, I know that was incredibly fast, but in a nutshell, that's what the product is like. If you wanted to, again, if you created a model, you could then, select the schedule, the job, or if you go into your buddy's, notebook and you end up screwing something up, you can use the reversion history to take a look at that. So I'll kick it back over to Remy. I appreciate getting the chance to show off our product and highlight some of those components which makes solutioning and implementing big data and analytics much more risk averse, much more reliable, and then sustainable going forward too.
All right, thanks, Mark. So we don't have too much time, so I'm actually just going to take one question. Everyone else's questions, you can please pose them to me. My email again is remy@caserta.com. So the question I'll take is, how long would a project like this take? Joe, that might be a good one for you.
Sure, I could take that. So this particular project that that these guys just walked through took about 5 or 6 months, and most of that time really was doing the data discovery and the identity resolution. That took a lot of profiling and a lot of trial and error, coming up with the matching algorithms. Doing the ingestion, building the models, that stuff took surprisingly not a very long time. Standing up the infrastructure took almost no time. The time really is spent dealing with the data, and cleaning it up and getting it matched and then stitching it together to feed the models. And then the models, the models went through a few iterations with the business to make sure that they were sensible. But if we were to build a bell diagram of the time spent, right in the middle would probably be building the part, matching the customers across all the different channels.
All right, we actually have time for one more question then. So what is the difference between EMR and Databricks? Mark, do you want to take that one?
Yeah, I sure do. The difference is that Databricks, our runtime, or the performance of our compute engine, takes advantage of years of reliability and performance tuning that are proprietary to our product. They're all under the hood, so you wouldn't really notice them as you're doing your development work. Whereas EMR, it relies on open source Spark, so it tends to be less performant than our Spark, which for a lot of our customers is a big deal to them because the amount of time you keep the clusters and the EC2 instances on, you're incurring a cost. So you want to be lucrative with the amount of time you're spending turning on your clusters to your computation work. And a lot of folks prefer to go with the more performant engine.
All right. Thank you, Mark, and thank you, everyone, for attending the webinar, and to our hosts. Again, if you have any further questions, please email them to me, and we'll get you a response. And anyone who answered questions in the room that we didn't address, we're going to answer you individually. Thank you, everybody. Take care.